reading over the weekend or your, I don't know, next couple weeks, you're welcome to read the lessons we skipped, and there's different ways to find area under a curve. There's a trapezoid. There's a left justified rectangle, right justified rectangle. It's kind of like this situation. And you're welcome to read that and study it if you like on your own time. But we kind of skipped that. And here we're going to talk about another way to calculate area under the curve. Okay, so consider dividing this region, area under the curve, into little rectangles. And the distance between each rectangle is delta x. So this would be delta x1, because it's the first rectangle, delta x2, and so forth. Now to do a proof, we need to look at the ith rectangle. Ith. The ith, or the nth rectangle. Like the letter I, yeah. To prove it for all cases, okay? So what happens is, so these rectangles are all on the left side of a point. So what happens is some of them are going to be a little bit above the curve, some of them are a little below, so it's going to average to be really close. Now, especially if we make our rectangles really, really, really small. If they're really tiny, it's going to approximate the area of the curve almost perfectly. So if we consider one representative rectangle Ri, so that's this guy here. And so this f of xi is right there, sorry. And this is x of I. That kind of got positioned weird. So that's the y value right here. I guess I can mark it. F of xi. Whose right side is defined by x equals xi. We see that its width is delta x, and height is f of x times I. So we're going to use area of a rectangle formula. So if we add up all these rectangles, we're going to get an approximation for the area under the curve. So I have to write down something here. So the area for our ith rectangle, how do I get the area for this rectangle here? Yeah, so length times width. So, or height times the base. So f of x is our height, and our base is delta x of I. Yeah, length times width. So this is length times width. So what we want to do is to get our area from A to B is we're going to take the sum of all these boxes. So the sum from I equals 1 to the last one, which is n, I equals n, of all these areas, all these individual areas for all the boxes. And we're going to sum them up, and that's going to give us the area under the curve. And this area, we already decided, was length times width. F of x of I times delta xi. Remember this symbol? Have you seen it before? Yes. Summation formula. Do you still use it in sequences and series in grade 11? No? Grade 12? We did in this year, right? Sequences last year? Yeah, great. Okay, so when the width, delta x, of each rectangle is made progressively smaller, as a consequence, the number of rectangles will increase. So we want to get basically almost infinity rectangles. The total area of the rectangles better approximates the area under the graph. In fact, there is equality at infinity. So area from A to B would then be equal to the limit as n approaches infinity. So the number of rectangles are going to approach infinity. We sum from I equals 1 to n. So that would be infinity. F of x to the I times delta x of I. Length times width. The infinite sum is called the integral function. So when we do the integral function, we're doing actually the infinite sum of length times width of all these little rectangles. So it's an elongated S because it's an infinite sum. So S, it actually comes from sum. Yeah, as a symbol for integral, it's not an I, it's an S for sum. Since it represents a sum. So we can represent the sum as follows. So area from A to B, which is equal to the limit as our number of boxes, right, n approaches infinity, and we sum up all these boxes from the I equals 1 to I equals n, so our infinity boxes of length times width, times. And that is equivalent to, I'm going to show you something, so how we would write this sum. So another way we can write this sum is the infinite sum. Okay, that's the integral symbol. So this is our f of x. Length is f of x times the width dx, change of x. And that's length times width, so infinite sum of the length times the width. Y times x, or change of x actually. And so essentially though, area under the curve is still the antiderivative. So it's just a different notation talking about the infinite sum, another way to calculate. So the integral is also the antiderivative. Follows at the integral is also the antiderivative. Okay, so the integral of f of x dx is equivalent to the antiderivative of a function. Now, there is a difference because not all integrals represent area. Okay, so an area, if you had some below the curve and some above, we had to break it up, right? When we do integrals, it doesn't always represent area. So for example, if I looked at the integral from 0 to 2 pi of sine x dx, well, that graph, this is 2 pi, you have some above and some below. So when you evaluate the integral, it equals 0 because the amount above and the amount below cancel each other out. So it doesn't always represent area. That's something to note. If you're looking for area, you have to use the antiderivative and separate it, right? Where's above the axis, where's below the axis. So the function f of x is referred to an integrand. And if you want more examples, so area, not all integrals represent area. So if you need some more examples, you can see page 495 of your textbooks. Example 1. Okay, so everything still applies that applied before. So if we're finding the antiderivative, it's the same when we find the derivative. So this dx here is, remember, we're doing the sum of length times width. So that width is our change of x. So this is our f of x right there. That's our f of x times dx, length times width. So when we actually find the antiderivative, we use the same rule. So what's the power rule? X to the n. What's the antiderivative of x to the n? to the n plus 1 over n plus 1, or 1 over n plus 1 times x to the n plus 1. All right, these all apply. Oh, because then it's 1 over x, which the antiderivative is natural log of x. Right, x to the negative? Yeah. X can equal negative 1. Then it would be 1 over x. Yeah. Okay, sine x dx, what's the integral, our antiderivative? So that's your change of x. So we're doing this, remember this is length times width. So we're doing the sum of all the rectangles of length times width. So your length is your function, that's your f of x, and times, this is my change of x. So it's very, very, right? So it's just notation. So this is really your f of x, what you're actually anti-deriving, sine dx. So the derivative of negative cos is sine, so then negative cos x. Yep, Graham? Or is it just relaxing here? Okay. Cosecant squared x, what's the antiderivative? Cotan? No? What is it? Cotan. Okay, negative cotan? No, regular cotan. Hey. Cos would be? No, just sine, yeah. Just be sine. So backwards. Secant tan? Secant. Oh, this one you guys should know. Secant squared. 10. Maybe you don't know. Cosecant cotan would be cosecant? It's not negative, it's negative cosecant. It would be negative cosecant. Negative cosecant. Okay, properties of, so these are the same. If you have a constant times a function, so like you had 2 sine x, right? It would be 2 negative or negative 2 cos x, yeah? So again, going back here, the dx is the width. So we're doing length times width. So what we're doing here is the infinite sum of all these rectangles, and the rectangle area is length times width. And so our width, or this delta x, can also be called dx, change of x. Okay? Okay. So it's part of the notation. So if we have a constant, it's the same thing as the constant, the integral of f of x dx. Summation, right? We integrate each one individually. Okay, so finally, the fundamental theorem of calculus. A definite integral occurs when you evaluate an integral, the result is a number. So if we're actually evaluating between two values, right? I want the area between, or the integral between 1 and 5. Kind of like the area between 1 and 5. But area is not always. So how we would write this is we're going from A to B. So A would be on the bottom, B would be on the top, to show what numbers it's between. That's a B, can you tell? There you go. A to B of f of x dx would equal to, because we're evaluating it, we don't have to worry about C, of course. So f of b minus f of a. Okay? Or you could also write it as, there's another way, f of x from a to b is another way to write it. You might have seen that notation before. It's a common notation. I'll show you, I'll do an example with that so you can just get used to that notation.
Why are there multiple locations for this?
Yeah? I have to do it now, yeah. Okay, so A and B are called the limits of integration. A is called the lower limit, and B is called the upper limit. So an indefinite integral goes this, a definite integral results in a number. An indefinite integral results in a function. Okay, so indefinite gives you a function, it's like antiderivative, whereas we're going to actually get a number answer for a definite integral. Also, I should note that our indefinite integrals must include plus c. So plus c. I just didn't write it for those ones. Okay, so let's find the indefinite integral. Okay, so this guy, the indefinite integral of cos x dx, what does that equal? Sine x plus c. Okay, so this guy, we're going to take the integral of each one, right? So if you integrate 3x to the 4, we're really anti-deriving it. So what are we going to do with the x to the 4? Add 1, so it'll be x to the 5, and then the 3 over 5. Plus 8 becomes 8x plus c. Okay, so in a definite integral, why do we not need to include plus c? No, they cancel out.
Wait, so how is this different?
It's not. So it's just teaching you a new notation. Hooray. So that's nice, right? Shouldn't be stressful. Okay. But areas and integrals are not the same thing. So the nice thing is, with integrals, you don't have to draw a picture, figure out where's above, where's below, right? We just can integrate it. We can just find the value. Don't have to draw a picture. Yeah. Not always the same thing. Sometimes they are. Okay?
That should be our final exam.
You guys are ridiculous. Okay, so cos of x. What's the antiderivative of cos? We just found this. Sine x. And we want to evaluate it from pi over 4 to pi over 2. Okay? We do. So that's saying from pi over 4 to pi over 2, which is equivalent to, so which one's going to go first? Larger minus slower, lower. Minus slower. Yeah. Okay, so sine of pi over 2 minus sine of pi over 4. Okay, let's see how your trig skills are working. Sine of pi over 2 is 1 minus root 2 over 2. So it'll be 2 minus root 2 all over 2. Okay, so we already integrated this before, right? We found it to be 3 over 5 x to the 5 plus 8x. Do I need the plus c? No. And we're evaluating it from 1 to 3. From 1 to 3. 1 to 2. Yes, Bennett? No. That you can't do that, right? Because of subtraction. So I just got a common denominator. Yes, if there's a 2 minus 2 root 2 over 2, that sure is a lot of 2's. Okay, so now we want to find 2 minus 1. So 3 over 5 plus 8 times 2 minus, I'm going to lower this, so 1. 3/5 Okay. Okay, so 2/5 to the power 5, I mean, 32. 32 times 3, 96 over 5 plus 16 minus 3 over 5 minus 8. Okay, so that gives us 16 minus 8 is 8. And then a 93 over 5. And then, so that's 40 over 5. Which equals 133 over 5. Who needs a calculator? Not us. Okay. Hooray! Hooray! So, okay, we could. Or do you want to do the homework and finish it in class? All right. Okay. So stop